Hello! So far, we have proved that any nim game is equivalent to a nim game of a single pile. We will now try to extend this to all impartial games. But first, we need to note that being equivalent does not mean that they play in the same way. For example, we have previously seen that star 11 plus star 13 is equivalent to star 6. We want to move to star 11 plus star 11, which is equivalent to star 0, by removing 2 chips from star 13. And on the right hand side, it is equivalent to removing all 6 chips. But there are other moves in the game. Say we move to star 11 plus star 8, which is equivalent to star 15. So we are removing 5 chips from star 13, but on the right hand side, it is equivalent to adding 9 chips. Or if we are starting with star 11 plus star 11, which is equivalent to star 0, any move on star 11 plus star 11 will increase the star 0 to something positive. And adding chips to stacks is technically not allowed in a nim game. We now introduce a variation on nim. A game of poker nim consists of a regular nim game plus a bag of B chips. We now allow regular nim moves and adding B prime chips to one pile. For example, we could be moving from star 3 plus star 4 to star 53 plus star 4. It sounds like there are so many more options now. But do the extra options matter? How does this change the game of nim? And the answer is nothing has changed. Say we are facing a losing game, so any regular nim move would lead to a loss. In poker nim, we are now allowed to add some chips to one pile, so we do that. So what would be the move that the opposing player will make? The opposing player will simply remove the chips we have placed, and nothing has changed. We are back to the original state where we are facing a losing game. So adding chips is a reversible move and has no benefit to any player. The possibility of increasing a pile does not change the game. So then technically, when we say that a game is equivalent to a nim game with one pile, it's actually a poker nim game with one pile. Now suppose we are in a different situation and we have a game G that has options equivalent to star 0, star 1, star 2, star 5, star 10, and star 25. We claim that G is equivalent to star 3. Let's see why that is. The options of star 3, which are star 0, star 1, and star 2, are all available as options for G. If we add chips to star 3, then the opposing player can just remove them to get back to star 3. But how do we get this number 3? It is the smallest non-negative integer that is not an option of G. So we give this definition. Given a set of non-negative integers S, the max of S is the smallest non-negative integer not in S. Max stands for minimum excluded integer. So in our example, the max of 0, 1, 2, 5, 15, and 25 is 3. And the max function is the critical link between any impartial games and nim games. And here is a related theorem. Let G be an impartial game, and let S be the set of integers n such that there exists an option of G equivalent to star n. Then, G is equivalent to the star of the max of S. We will illustrate this with an example. Let's take a look at star 1 plus star 1 plus star 2. There are essentially 3 options. Star 1 plus star 2, which is equivalent to star 3, star 1 plus star 1, which is equivalent to star 0, and star 1 plus star 1 plus star 1, which is equivalent to star 1. So by our theorem, star 1 plus star 1 plus star 2 is equivalent to the star of the max of 0, 1, and 3, which is then star 2. And we can easily verify that this is true using our previous results. As an exercise, show that a game cannot be equivalent to one of its options. And here is a proof for our theorem. We let n be equal to the max of s. And it suffices to show that g plus star m is equivalent to star 0. That is, g plus star m is a losing game. So from g plus star m, there are two possible moves. We can either move on g or move on star m. In the first case, suppose we move to g plus star m prime, where m prime is less than m. So what would be a correct move for player 2? We see that since m is equal to the max of s, there exists an option g prime of g such that g prime is equivalent to star m prime. So player 2 would move to g prime plus star m prime. This is a losing game because g prime is equivalent to star m prime. So g plus star m is a losing game for player 1, and g plus star m is equivalent to star 0. In the second case, suppose we move to g prime plus star m, where g prime is an option of g. Can you show that g prime plus star m is a winning game for player 2? We see that g prime is equivalent to star k for some k that is in S. So g prime plus star m is equivalent to star k plus star m. But this is not equivalent to star 0 because k is not equal to the max of S. The max of S cannot include anything that is in S. So g prime plus star m is a winning game for player 2. This means that g plus star m is a losing game for player 1. And therefore, g plus star m is equivalent to star 0. And that completes our proof. A consequence of this theorem is what we are aiming for this entire term so far, and it is called the Sprague-Grundy theorem. It states that any impartial game G is equivalent to a poker-nim game star n for some n. We will give a slightly sketchy proof here. If G has no options, then G is equivalent to star 0. If G has options, say they are G1 to Gk, then, by induction, each of the Gi's is equivalent to star ni for some ni. Then, by our theorem, G is equivalent to the star of the max of n1 to nk. And that completes our proof. So this means that any impartial game has a number. But how can we find these numbers? And how does it help us find winning moves in these impartial games? We will discuss this in the next lecture.